Hello, everybody. We are Team Security Breachers doing the project Malware Detection using Hardware Performance Counters, also known as HPCs. I'm Kenneth Chen with my teammates Daniel Haran, Alejandro Torres, Nicholas Tran, and Shruti Gaikawari. First, an introduction. Modern processors face threats from many increasingly complex forms of malicious software, also known as malware. Ways to detect these malware have some limitations. Some detection services are only able to detect well-known malware. Hardware performance counters are specialized registers in a CPU used to monitor and measure aspects of a computer's performance. This project aimed to test the use of HPCs to detect malware by creating some simple malware and benign software, also known as benign, and using HPC to measure their performances.
Okay, just to give a little bit of background, there are some malware that intentionally harm machines by the following. They steal sensitive data, they damage security measures, and they are able to access unapproved systems to cause financial losses. In order to combat these, we use HPCs, which can be read by sampling events at irregular intervals, and polling, which can be read instantly but must be configured properly. HPCs provide low-level insights into computers' hardware operation. However, they do come with several advantages and disadvantages. Some advantages include real-time monitoring, they're able to monitor micro-architectural events, and they have the potential to monitor system behavior with less overhead. Some disadvantages include the overcounting and their non-deterministic nature.
For this project, we decided to use a generic ransomware. In real-life situations, attackers would attach it with other files or mask it as benign-ware, so user would open it accidentally. So what ransomware usually does, it just locks user's computer or encrypts all the files in the system. So the only way to recover them is getting a passcode from an attacker. Usually attackers will ask money or any valuable information in return. So for our encryption, it's performed only on a desktop path, just for safety reasons. It makes sure it doesn't encrypt itself or the key or the decryption file, because if one of those files get encrypted, then you can't recover anything. And the decryption pretty much does the same thing, but it decrypts all the files using the secret phrase. Okay, so as our benign-ware, we chose backup recovery scripts, so they behave similar to the ransomware. On the left-hand side, you see our backup script. It goes through the same desktop path and pretty much backs up every file except for itself and a recovery file in a specific folder. And a recovery file, whenever you want it, you can just trigger it, and it will recover all the files from that folder to the desktop.
Okay, so here's an example output of an encryption script that we ran. So you can see below, we were able to receive some data for the performance stats. On the right-hand side, we see some of the important data that we were able to collect with the commands shown. Some of the important commands that we focus on are cache misses level 1 and level 3.
This is our data collected on the software created for. We took the averages of the instruction cycle, the cycles, instructions per cycle, CPU spikes, context switches, and cache misses for level 1 and level 3. A particular note in the data are 3 categories: the CPU spikes, level 1 cache performance, and level 3 cache performance. The benign-ware values were drastically higher than the malware equivalent. Level 1 caches misses were approximately 3 times higher in the benign-ware backup stage than the malware encryption stage. Benign-ware level 3 cache misses and CPU spike cycles were approximately 4.5 times higher than their counterparts in the malware program.
So overall, some of the lessons that we learned throughout this project were how to collaborate to research various sources, how to test our methodology, and then finally to create a report. So throughout this project, we learned in-depth Linux knowledge and all about HPCs and how they can be used for malware detection. Some of the cons of the project were that the final data that we collected using simple malware and benignware might not be able to be extrapolated to more complex programs. So for example, if the ransomware programs are more complex, then the different parameters might have very significant differences compared to the outputs that we got. And also the HPCs might have also have different results of the same execution of our malware and benignware softwares on different machines due to different architectures utilized. And finally, in conclusion, our level 1 and level 3 cache misses, along with CPU spike cycles, were very crucial in differentiating malware and benignware softwares. The HPCs enabled the detection of potential malware attacks through hardware performance metrics. The HPCs also provided valuable insights into malware and benignware execution. So when we focus on cache misses and CPU spikes, we can enhance malware detection capabilities.
Thank you for watching. Here is a page of our references.